Hello and welcome to this video brought to you by Smart Exam Resources. In today's video, I shall explain to you the concept of oxidation, reduction and redox reactions. So before I explain to you the concepts of all of these, I'll try to tell you a few ways of remembering at least two definitions. So first is the oil rig. Obviously, you must be aware of the word oil rig if your teachers must have taught you. Else, if it is new, you can pay attention. So O stands for oxidation. So oxidation is what? Oxidation is loss. And loss of what? Loss of electrons or loss of hydrogen. So you can define oxidation as loss of electrons or loss of hydrogen. So I'm writing it down here again. So this is oxidation. Why am I writing it down here? Because there are totally 4 definitions of oxidation. So one is it is loss of electrons. Secondly, it is loss of hydrogen. And reduction. What is reduction? So R stands for reduction, and reduction is just the opposite. It is the gain of electrons or hydrogen. So let me just jot the same thing here. So this is about reduction, and we just saw that reduction is the gain of electrons or it is the gain of hydrogen. So I have 2 definitions in place. Now what about the other 2 that I was talking about? Well, the other 2 are also simple, but there's no mnemonic, so I'll just write them directly here. So oxidation is also a gain of oxygen. It's a gain of oxygen. Just the opposite. What is reduction? Reduction is the loss of oxygen. And then the last definition, it is an increase. So it is an increase in the oxidation state or oxidation numbers, you may say. So reduction is the opposite. It is a decrease in the oxidation state or oxidation numbers, again, like I told you. So these are the 4 definitions of oxidation and reduction. So what do you mean by redox? Well, redox refers to a reaction in which oxidation and reduction take place simultaneously. So with this basic info, now we are going to take examples of oxidation, reduction and see where redox reactions are also taking place. So that means where there'll be oxidation and reduction happening simultaneously. So let me take the example of the easiest one, and that is related to the loss or gain of oxygen. So let me just number the choices the way I'm going to explain the video. So this will be my 1. I'm going to explain oxidation and reduction in terms of oxygen. Whether it is loss of oxygen, gain of oxygen, let's see that. So now I'll take the first example as Fe2O3. So Fe2O3, iron oxide. So if I'm going to reduce this iron oxide with the help of carbon monoxide, I just said that. I shouldn't have said that. Fine. So suppose you do not know that I'm going to reduce iron oxide with the help of carbon monoxide. But yes, if I'm going to react carbon monoxide with iron oxide, what do I expect? I expect 2 products. One of them is iron, next is carbon dioxide. Now let me balance it. So this is 3CO, this has to be 2Fe, and this is 3 CO2. Okay, now if I have to see a relation between my reactants and the products, what am I going to do? I'm going to simply connect my reactants and products the way I'm doing it with the line. So now here, what's happening is Fe2O3 has changed into Fe. So here what is happening, there's a loss of oxygen. And what did we just see? If you look at the definitions on the screen, reduction is the loss of oxygen. So in this case, iron oxide got reduced. So this is an example of reduction. Okay. Now if I talk about carbon monoxide and carbon dioxide, what's the relation? So well, these two are related by the opposite. And what does it mean? Well, it means that carbon monoxide has gained an oxygen, so it has undergone oxidation. So this is an example of oxidation. So aren't oxidation and reduction taking place simultaneously? Yes, they are. So what can you say about this? Well, obviously you'll be saying that this is an example of a redox reaction. Redox because the two reactions are taking place simultaneously together at the same time. Okay, cool. So now I'm going to take another example, and that example is, sorry for that, and the example is about the, I can just take another color. Okay, reaction between copper oxide and magnesium. So when copper oxide and magnesium, they react, what are the products? The products are copper and magnesium oxide. Okay, any balancing required? No, it's already balanced. Okay, so now again I'm going to find out whether it's oxidation or reduction. So I'm going to connect the copper oxide and copper, and what do I find? Well, I find that copper oxide has lost its oxygen. So it means, is it an oxidation or reduction? Yes, this is an example of reduction. Why? Because copper oxide lost oxygen. Similarly, let me see if I can find a relation between magnesium and magnesium oxide. So these two, how are they related? So magnesium has gained an oxygen on the product side. So this is obviously an example of oxidation. So once again, oxidation reduction take place simultaneously. So this again is an example of a redox reaction. Okay, so I can call this as a redox reaction. This again is an example of a redox reaction. Fine. One more example, come on. So this time I'll again change my color to say what? Say yellow one. Okay. So now if I talk about the reaction between copper and oxygen. Okay. So when copper is heated in the presence of oxygen, what happens? I get copper oxide. Any balancing needed? Yes. I need to put in 2 over here. Why 2? Because oxygen is 2. So in this case, copper oxide, this becomes 2 as well. Okay, so now let me see how these are related. So here if you see, there's a straight away addition of oxygen to copper, and this is an example of oxidation. Yes. And why oxidation? Because simply oxygen has been added to copper. Fine. And I'm going to take my last example, because I'm very sure by now you must have understood the concept of oxidation, okay, and reduction, and obviously redox. So now I'll take my green color back, and this time I'll take the example of magnesium. So when I talk about magnesium, if I heat magnesium in the presence of oxygen, what do I get? I get MgO. And any balancing needed? Yes, this becomes 2, this becomes 2. Okay, now it's balanced. Here again, once more, there is simply addition of oxygen, and therefore we say this is an example of oxidation. Cool. Brilliant. Okay. So we are done with the example involving oxygen. So now we know that there are 4 different ways of explaining the concept of oxidation and reduction. So I'm going to deal with them one by one. So now let me just separate this. Okay, cool. So now talking in terms of what? You want me to do hydrogen, loss of electrons, or gain of electrons, or you want me to explain the reduction oxidation in terms of what? Look at the last option. It's oxidation state. Yes. Now I feel I should be explaining to you the concept of the oxidation state first before I even explain to you what is meant by the increase in the oxidation state or the decrease in the oxidation state, because if you do not know, you won't be able to answer the questions. And also exams will have questions based on calculating the oxidation state of ionic compounds or covalent compounds, right? So what I am going to do now is I'm going to explain to you the concept of oxidation state. Fine. So here I have written down the definition of the oxidation state. And what does it tell you? Well, it tells you it is the apparent charge that an atom has in a molecule or ion. So why have I written here specifically molecule or an ion? So let me just explain to you, because when you have to find the oxidation states, you don't have to only find the oxidation states of ionic compounds. It is also quite possible that you will be asked to find the oxidation state of methane. Now you will be surprised. How, when there are no charges? Well, the thing is, since this entire thing, the concept of finding oxidation or reduction in terms of oxidation state is being used, so definitely we will have to consider the covalent compounds also. Okay, so then there are basic rules that you need to keep in mind when you're dealing with covalent compounds. Once you keep that in mind, you'll never make errors. I'll explain to you how you have to deal with covalent compounds. Okay, so when I talk about a molecule, I'm referring to any kind of covalent compound that is present, and ion also. So basically it is the apparent charge that an atom has in a molecule or an ion. So now, how do you write the oxidation states basically? So usually there are two things that are involved. So if I have to write the oxidation state, for example, of say oxygen. So you know, oxygen needs 2 electrons to gain 2 electrons to complete its octet. So if it is gaining 2 electrons, so what is happening basically? The charge on it is becoming negative. Okay, it's accepting electrons, so it's becoming more negative. So the charge on oxygen becomes -2. Okay, so now you'll wonder whether to write -2 or 2-. There'll be this confusion. Well, in the IGCSE you might or might not lose marks for not writing this properly, but in the higher grades definitely you must keep it in mind. So what's the difference if I write -2 and if I write 2-? Well, this tells you about the charge. So when I write 2-, it is just a charge. So I can write O2-, I can write H+1. So what is H+1 and what is H2-? These are charges. Okay, but when I talk about -2, that is specifically I'm talking about the oxidation state. So there's a difference. One refers to the oxidation state and the other refers to the charges. So whenever you write the charges, you're going to write the number, the value followed by the sign. And whenever you write the oxidation state, it has to be the number preceded by the sign, or the value preceded by the sign. Okay, so since I'm explaining to you the oxidation state, I'm going to write the sign first and then followed by the number. You have to keep it in mind. And if you follow a proper procedure, when you go to your IBDP or A levels or whichever boards you want to migrate to, you'll never lose your marks for such kind of things. These are basic things you need to know. Fine. Okay, so two things are present for an oxidation state, is the sign and the value. So I'm just going to write that a sign is important and there is a value which is important. Okay, so what is the sign going to be, positive or negative? Well, the sign can be either. It can be a positive, it can be a negative sign. So when there is a positive sign, it means that the atom has lost an electron, right? And when there's a negative sign, it means that the atom has gained an electron, right? So now, and what is the value talking about? Value refers to the number of electrons lost or gained, because you're going to talk in terms of loss or gain of electrons. So that value is going to tell you how many electrons are lost or how many electrons are gained. So it simply tells you the number of electrons lost or gained. Now, why am I writing lost or gained? I really do not know. It's a positive sign or a negative sign. Like I told you on the top, if it's a plus sign, it indicates that the atom has lost electron, and if it's a negative sign, it's going to say atom has gained an electron. So depending on whether it is losing electrons, gaining electrons, sign is going to vary. So, but definitely for sure, I know the value tells me whether the number of electrons are lost or gained. Fine. So keeping these two things in mind, now I'm going to teach you how to calculate the oxidation states of atoms, okay, in molecules or an ion. So let me just tell you to begin with, whether it is the oxidation state of a covalent compound that you're finding out or an ionic compound that you're finding out. Treat the covalent compound like you would have treated the ionic compound. Okay, don't treat the covalent compound as a covalent compound. Think of the covalent compound as an ionic compound. You'll understand what I'm trying to say once I give you examples. Okay, so to begin with, if I talk about methane, okay, you know methane, the formula for methane. If you have yet not studied the formula for methane, not studied the organic chemistry, you won't be knowing the formula for methane, but it's still fine, I'll tell you. So methane is CH4, and methane is technically a covalent compound. So the compound that is formed by sharing of electrons is a covalent compound, right? So now over here, how do I find out the oxidation numbers? So now the simple thing is, since it's a covalent compound, the charge on the covalent compound is 0. I'm talking about the total charge, okay? So if I talk about the total charge on my methane, I have to think about the total charge as being equal to 0. That's how I'm going to imagine this. So now I know hydrogen has just 1 electron. It can either lose 1 electron, it can either gain 1 electron. So I'm going to treat this hydrogen as being 1, okay, and then I'm going to write 4 into 1 because there are 4 of hydrogens. I do not know how many carbons are there. I'm going to write it, sorry, what is the charge? I do not know the oxidation number of carbons, so I'm just going to write it as X, and I know the total charge on this molecule is 0 because it's a covalent compound, so I'm going to write it as 0. That gives me X plus 4 equals 0 and X equals minus 4. So what is the oxidation number of carbon? So the oxidation number of carbon is what? So oxidation number, I'm going to write it down here. So oxidation number of carbon equals minus 4 and hydrogen equals plus 1. Okay, that's one thing, right? Now next I'm going to give you another example, and that example is going to be of so now before we take some more examples, I'll be making you go through this little write-up that I've put on the screen. And what does it tell you? Well, it tells you that the oxidation numbers of group 1 elements, that is lithium, sodium, potassium, rubidium, cesium, francium, are all plus 1, and the group 2 elements, that is beryllium, magnesium, calcium, strontium, barium and radium, the oxidation number of these elements is always plus 2. So what do you observe? You observe that the elements in group 1 and 2 will virtually always have the group number as their oxidation numbers. Okay, so whatever is the group number is going to be the oxidation number. So group 1 will have an oxidation number of plus 1 and group 2 elements will have an oxidation number of plus 2. Now below what have I written? Well, below I have written that the maximum oxidation numbers, now please be careful, I'm not saying the oxidation numbers, I'm using the word maximum oxidation numbers. Now what do I mean by the word maximum oxidation numbers? That means there can be other oxidation numbers as well, but when I'm telling you the word maximum oxidation numbers, means I'm saying whether there are other oxidation numbers or no, but if there are more than one oxidation numbers, then there are certain rules that you need to keep in mind. So for example, the maximum oxidation number for group 1 is always going to be 1, For group 2 is going to be 2, group 13 is going to be 3. Now from here onwards, it's very simple. You just take the group number. So whatever is the group number, from the group number you minus 10 and you get the oxidation numbers. So group 13 is 13 minus 10, which is 3. Group 14 is 14 minus 10, which is 4. Similarly, group 15 is 5. Group 16 is 6. And group 17 is 7. So what is the meaning of the word maximum oxidation numbers? Well, the thing is that it is not possible to lose more electrons than there are in the outer shell. So the maximum possible oxidation number for a group 16 element is plus 6, because there are 6 electrons in the outer shell. So basically what are they trying to tell you? That the oxidation number can be maximum. Now you see what I mean to tell you exactly is, whenever you talk about a range of values, okay, so the range is from negative to positive. So obviously when I'm going to talk about maximum oxidation numbers, I'm going to talk about the positive values. Now here it means that it is not possible for an atom to lose electrons which are more than the number of electrons in the outer shell. So for example, look at the group 1 element. Okay, if I talk about sodium, I'm taking an example of sodium. Now I know sodium has an atomic number of 11. Okay, electronic configuration is 281. That means it has got 1 electron in the outermost shell. Is it possible for sodium to lose more than 1 electron when it is combining? No. It is always going to have the valence electrons which are involved in the forming of bonds. So the maximum oxidation number for group 1 element is going to be 1 only. So now look at the group 4. Okay, sorry, the group 14. Here it is said that the group 14 elements can have a maximum state of oxidation number of plus 4. Now can you think of an element which is present in the group 14, which is very common in your reactions? Just think. Well, I hope you've thought about the very common element that you'll be coming across, and that is your carbon. Okay, I'm giving an example of carbon. Now what is the atomic number of carbon? It is 6. What's the electronic configuration? 2, 4. How many electrons are there in the outermost shell of carbon? Well, you can see there are 4. So carbon can lose 1, can lose 2, can lose 3, or can lose all its 4 electrons. It's still fine. But can it lose beyond 4 electrons? If at all. I'm talking about losing. No. It cannot lose more than 4, because there are only 4 electrons in the outermost orbit. So when electrons are being lost or gained, okay, or shared, what is the total actual idea? The idea is to form a stable octet. Okay, definitely there are incomplete octets which are also stable, but then we'll talk about those later in the higher grades. As of now, you need to focus about, in the grade 10 syllabus, you only need to know that whenever atoms are losing electrons or gaining electrons or sharing electrons, they do so that they become they get the stable electronic configuration of a noble gas. Okay, so now over here there are 4 electrons in the outermost orbit of carbon. So carbon cannot lose more than 4. So the maximum oxidation number for carbon is going to be 4. Okay, so if it loses all 4, is going to be plus 4. If it loses 3, is going to be plus 3. If it loses 2, is going to be plus 2, loses 1, is going to be plus 1, etc. Okay, or if it gains 4, is going to be minus 4. Are you getting what I'm saying? Yeah, that's what it is. So technically speaking, you need to remember that the maximum oxidation numbers mean this. It means nothing else. It is telling you the maximum. I'm not telling you there is only one oxidation number for group 4 which is plus 4, or group 15 is plus 5. But the maximum in any case is going to be equal to the number of electrons in the outermost shell, and that is equal to the group number for groups 1 and 2, and it is group number minus 10 for groups 13 to 17. Okay, so I hope I'm clear in this. So I'll just explain to you some examples. Okay, and while doing examples, I'll just tell you the rules. If I tell you all the rules at one time, it'll be super confusing. Okay, so let me take an example. So the first example that I'll be taking is of sulfur dioxide. So suppose you have sulfur dioxide. Now you know sulfur dioxide is supposed to be a covalent compound. So I'm writing it down here. Every time you need not write it down. So this is a covalent compound. Okay. So if it's a covalent compound, obviously it's not going to have an overall charge. So if it's a covalent compound, the overall charge is going to be 0. Okay. So this is going to be the overall charge. Okay. So now what is the next thing? How do I find out the oxidation numbers for oxygen and sulfur? Well, in this case we need to see which is the more electronegative of the two, and obviously, as you know, oxygen is more electronegative, okay, compared to sulfur, and therefore this oxygen is going to be assigned its normal valency. And what do you mean by I'm going to assign its normal valency? I'm going to assign it the valency that the charge that it would have in an ionic compound. So suppose if oxygen was present in an ionic compound, what kind of a charge do you think would have been present on the oxygen? Obviously, you know the atomic number of oxygen is 6. So it is 2,4. Sorry. Atomic number of oxygen is 8. It is 2,6. So if it is electronegative, it is going to pull 2 electrons towards itself. So therefore it is going to have a charge of -2. So what am I going to do? I'm going to give it a charge, okay, of -2. And like I told you, the charge is usually the oxidation number, okay. So in this case, because oxygen is electronegative, I'm going to assign oxygen its normal valency. So I'm going to consider it as being an oxygen being present in the ionic compound, okay, and then pulling 2 electrons towards itself. So in that case, I'm going to give oxygen a charge of -2. So the oxidation number is also going to be equal to the charge of oxygen, which is -2. And how many oxygens are present in sulfur dioxide? There are 2 oxygens present in sulfur dioxide. So I write a number 2 ahead of it, and plus, and I do not know the oxidation number of sulfur. I'm trying to find this out. I'm going to write this x over here, and the overall thing is equal to 0. So now if I'm going to solve this, it becomes x minus 4 equals 0 and x equals plus 4. So that means if I now have to ask myself what is the oxidation number, so my oxidation number of sulfur, obviously I have found this out to be plus 4, and that of oxygen, I assume that it is going to behave like an oxygen in the ionic compound, because oxygen is more electronegative compared to sulfur in this case, and therefore I took its normal valency, normal charge, and which I also took it as being the oxidation number. So now what do I have? I have both the oxidation numbers, and I have solved this sum. I found out the oxidation numbers, okay. So let me take another example, and this time I'm going to take sulfate ion maybe, okay. You're all aware of sulfuric acid. It has got the formula H2SO4. So I'm going to take an example of the sulfate ion. So if I write the sulfate ion as SO4 2 minus, okay, SO4 2 minus. So what's going to happen over here? Again, I'm going to talk about the sulfur and the oxygen. So which one is more electronegative? Well, I find that oxygen again is more electronegative. So again, I'm going to assign its normal valency to it, and therefore I am going to write -2 for oxygen, and over here it is O4. How many oxygens are there? There are 4 oxygens, okay. Plus, do I know the oxidation number of sulfur? I do not know. I'm going to put an X here. Now can you see it is SO4 2 minus? So this is not a covalent compound, it's an ionic compound. So I'm going to write the charge -2, okay, as my oxidation overall charge, okay, to the right. So that means whenever it's a covalent compound, overall charge is 0, but when it's an ionic compound, the overall charge is the one that is seen on the ion. So here it is seen as -2. So it's written as 2 minus. I'm going to take it as -2 over here. Now I'm going to solve this. So this becomes x, 4 into -2 is -8 equals -2. So this becomes x equals 8 minus 2. So x equals 6. So if I have to write the oxidation numbers, okay, what am I going to do? Once again, oxidation numbers for sulfur is +6 and for oxygen is still the same, it is -2. Okay, so can you see how easy it is to find the oxidation numbers? Only what you need to keep in mind is you need to see whether it is covalent or ionic. So here I'm writing it down as SO4 2- as my ionic. It has got a charge, so it is an ionic. Okay, so now if it is a covalent compound, set it equal to 0, the total charge equal to 0, and if it's an ionic compound, set the total charge equal to total charge on the ion. Okay, fine. I'll take another example. So the other example would be Cr2 O7 2-. Now in this case, what is going to happen is, we know the more electronegative atom is oxygen, and therefore once again the oxidation number of oxygen is going to be -2. So here I'm going to write the oxidation number of oxygen, which is -2. How many of oxygens are present? 7 are present. Okay, now here chromium is Cr2, it's diatomic, so I'm going to write this as 2 into, I do not know the oxidation number of chromium. I'm going to write it down as X. So 2 into X plus 7 into -2 gives me -2. Once again, I'm going to solve it for my X, and I get 7 into -2 is -14 equals -2. So this becomes 2x equals 14 -2. So 2x equals 7. Sorry, what am I doing? 2x equals 12 and x equals 12 divided by 2, which is 6. So if I ask you what's the oxidation number, so oxidation number of chromium, I just found it to be +6, and of oxygen I have already taken it to be -2. So here again I found out the oxidation numbers. Excuse me. Okay, I'll take another example, and I'm going to take the example of hydrogen peroxide, which is H2O2. Okay, now I know that once again this is a covalent compound, so it's not going to have any kind of charge. The overall charge is going to be 0, and I know that my oxidation number for oxygen is -2. Okay, so now let me see what happens over here. I know the overall charge is 0. I know it is 2 into -2, and then there are 2 hydrogens, so I write 2 into x. Let me solve this. So 2x minus 4 equals 0, and 2x equals 4. So x equals +2. So that means, what is the oxidation number of hydrogen? The oxidation number, I'm writing it down. This is an exception, please be careful. It's not a normal example. I have done this to just show you that every time you cannot take oxygen as -2. There are exceptions, and you need to know when not to take the charge as -2. Okay, the oxidation number as -2. So now over here it means that the oxidation number of oxygen, I have taken it to be as -2. That is still fine. We know oxygen can have a charge of -2 and oxidation state number of -2. But when I talk about that of hydrogen, now how many electrons does hydrogen have? Well, it has only 1 electron. So I'm writing this as +2. This means that hydrogen is losing 2 electrons. If it doesn't have 2 electrons, is it possible for hydrogen to lose 2 electrons? Well, no. So in that case, this is not how you solve it. So this was an exception, okay? Like I told you, you have to be careful. So now what do you do then in that case? So it's very simple. What I'm going to do is, I'm going to work it in the other way. Although oxygen is more electronegative, but it is with hydrogen, and with hydrogen I need to consider the case of hydrogen, that hydrogen cannot lose more than 1 electron. So I'm going to start with writing, okay, I'll just erase this and write H2O2 on the top again. So this is not possible. First I'm writing this down here, else you'll wonder why I miswrote it. Okay, Now again I'm writing H2O2. So when you have an example like this, okay, see that things are not getting violated, the rules are not getting violated. If someone doesn't have 2 rupees, how can he give 2 rupees to you? He should have 2 rupees to give you. It's the same logic. If I don't have like suppose an X number of rupees with me, I cannot give it to you. So in the same way, if there are not those many electrons present with that atom, the atom cannot lose those electrons, right? So I'm going to talk about this hydrogen. I'm going to write 2 into plus 1. Now this time I'm going to consider hydrogen for the reasons I told you. Plus I am going to now find out what is the oxidation state of oxygen in H2O2. So I do not know that. I'm going to write this down as X. Like I told you, it's a covalent compound. Total is going to be 0. So let me just solve it. So this becomes 2 plus 2x equals 0. 2 equals minus 2x. So in this case, my x becomes 2 divided by minus 2, which is minus 1. So did you see over here that the oxidation state of oxygen is not 2 in this case? It is going to be minus 1. Fair enough. Like I told you, coming back to the earlier example where I had mentioned a table here, and I had told you that oxygen, like maximum oxidation numbers. Now see, the logic applies. I had used the word maximum oxidation numbers, where I used the word maximum telling you that it is a maximum possible value for oxidation number, but it can be less than that. Okay, so in the same way over here, oxygen can take the value of minus 2, so also it can take the value of minus 1. Getting it? So this is how to interpret the above statements. Okay, I'll give you more examples. Let us take the example of the nitrate ion, which is NO3 minus. Now here again we know, compared to nitrogen, oxygen is more electronegative. So in this case, once again we are going to consider the oxidation number of nitrogen being unknown. So we are going to take it as X plus 3 into oxidation number of oxygen is how much? Is minus 2, and the overall charge is minus 1. So X minus 6 equals minus 1. X equals minus 1 plus 6. So X equals plus 5. So what is the oxidation number? Now I'm going to write it in short. Oxidation number of oxygen, well, I have taken it as being minus 2, and the oxidation number of nitrogen is, I just found it to be plus 5. Okay, so this was one more example. Also, you need to remember a few things more, and the rule is oxidation number of any uncombined element is 0. So that means if there is an element and it is totally uncombined, it has not combined with some other element to form another ionic compound or a molecule, so in that case it's the oxidation number is going to be 0. So what are the examples? Examples can be any. You can take hydrogen, oxygen, chlorine, bromine. If you find these kind of molecules, okay, existing, they are uncombined. Okay, so in that case, what is the oxidation number of the hydrogen in H2? It's going to be 0. So the oxidation numbers are going to be 0 for all of them. Okay, so have the oxidation numbers as 0. Okay, so now having understood the concept of oxidation numbers, let us see how you can use these oxidation numbers to identify whether a reaction is a redox reaction and where the oxidation or the reduction is taking place. Okay, so now for that I'll give you an example, a very simple example in which hydrogen gas combines with oxygen gas and gives you a product which is water, and water in the form of a liquid. So here, to balance it out, I'm going to add 2 here and then a 2 here. Okay, so now that I've taught you to find the oxidation numbers, you can quickly pause the video, and I will not again find the oxidation numbers. I'll just give you the oxidation numbers. Okay, so once you're done calculating, you can just get back to the video. So the oxidation number of oxygen, sorry, the oxidation number of hydrogen in H2. Now remember, I told you that on the top is just written that the oxidation number of any uncombined element is 0. So here you can see H2 is uncombined, O2 is uncombined, they are yet to react. So that means the oxidation number of this hydrogen is 0 and the oxidation number of oxygen is also 0. Okay, so we have these oxidation numbers. I'm writing them down here. So oxidation numbers. Okay, and here if you can see, when you try to calculate, you'll find that the hydrogen, like I told you initially also, cannot have a oxidation number of more than 1. It can either lose 1 electron, okay, or gain 1 electron. So now in this case, the oxygen is going to have the oxidation number of -2 here, and you can pause the video and calculate this. There's no harm in doing that. Okay, don't wonder if the previous video gave you an oxidation number of -1, why the oxidation number of oxygen here in water is -2. You calculate and you will be convinced. Okay, so now let me just talk in terms of oxidation reduction. So if I'm talking about oxidation reduction in terms of your oxidation numbers, so now how do I do that? Well, it's very simple. Just look at the hydrogen. Okay, what's happening to the hydrogen? Now here I'm just writing it down. This is for hydrogen, this is for oxygen. So when I talk about hydrogen to hydrogen, I'm going to compare the oxidation states. What do I find? I find that from being 0, it has gone to being +1. That means for hydrogen, the oxidation state has increased. And like I told you, the oxidation state has increased from 0 to +1. So here what is it? It's oxidation. So this is an example of oxidation. Excuse me. Okay, this is an example of oxidation where the oxidation state, so I'm just writing OS. Do not write OS, I'm just writing it in for short form. So oxidation state has gone from 0 to +1. Okay, so this is oxidation. Now what about oxygen? Okay, I have oxygen also. And if you see the state of oxygen, what has happened to oxygen? It has gone from being 0 to -2. So -2 is less than 0 if you see that way. So then in that case, the oxidation state has decreased. So this is obviously reduction. Okay, so this is how you use the oxidation numbers to identify whether a reaction is a redox, and if it's a redox reaction, then which element is getting oxidized or which is getting reduced. Okay, so over here I'll write it down for you, reduction, because the oxidation state has decreased. Okay, here I can say it has increased. See, I'm using all short forms. You do not do all of this in the examination, please. Okay, it has decreased from 0 to -2. Fine. So this is how it is. Giving you more examples, I get calcium solid plus SN2 plus gives you Ca2 plus Sn solid. Now you'll wonder what is all this. So I'll explain to you when I explain to you the ionic equations. So as of now, just consider the equation that is given to you. Okay, so what is seen in this? So if you observe carefully, calcium here is uncombined, so its oxidation state is 0, or oxidation number is 0, and Sn2 plus is 2 plus. That means it's a part of a compound. See, AQ means aqueous. Aqueous means it is a part, it's an ionic compound. Okay, it's a compound. Okay, and Sn2 plus has a charge, and Sn2 plus is in the aqueous form. It's a part of a solution. Okay, so that means Sn2 plus aqueous. So the charge on Sn2 plus is +2. On the calcium, again it's mentioned Ca2 plus. Again it is a part of a compound. Okay, dissolved in water, so aqueous. So the charge is +2. And again tin. Tin, you can see tin is a solid. Solid meaning it is the tin element has been formed. Okay, and it is in the pure state, so it is uncombined. It is having an oxidation state or oxidation number of 0. So now in this case, if I'm going to compare this equation for oxidation reduction, I can see clearly that calcium has increased its oxidation number or oxidation state from 0 to +2. So there's an increase in the oxidation state. So I can say this is an example of oxidation. Similarly, if I talk about SN2 plus going to SN, so from +2 it has gone to 0. So the oxidation number has decreased. So this is an example of reduction. So this is a redox reaction, and where oxidation and reduction is as shown on the screen. Fine. So I think these are enough examples to explain to you oxidation and reduction in terms of the increase or decrease in the oxidation numbers, right? So now I'll explain to you. Okay, let me just mark what we have done here. So let me just, okay, go back to the screen. 1 minute. Okay. Okay, so here we have finished with the gain of oxygen, loss of oxygen. Already we have spoken about the increase and decrease in the oxidation state. So the second one is also done. Now we talk about the loss of electrons. So I'm marking this as a third one. Okay, so now let's understand oxidation and reduction in terms of loss of electrons, okay, or gain of electrons. And for hydrogen we'll consider it last. Okay. So as you can see in this example which I've taken for oxidation, okay, oxidation is a loss of electrons, reduction is the gain of electrons, and the example that I've taken is 2Na solid plus Cl2 gas gives you 2NaCl. Okay, so let us understand what exactly is happening in this reaction. So as you can see to the left, I've written the electronic configurations for sodium and chlorine, which are 281 and 287 respectively. So as you can see, the sodium will be happy to lose this one electron, while chlorine will really want to take that one electron to complete its octet. So by losing one electron, sodium is able to complete its octet, okay, and by gaining that one electron, chlorine is also able to complete its octet. So now what is happening exactly? If I write the half reactions, okay, the half reactions are basically what, sorry, the half equations I mean. So I'm going to write it on the top here, the half equations. The half equations means what is happening at one end, okay, that's what you say. If it's a electrolysis, you say what's happening at one electrode, okay. So now over here for sodium, what is happening? Sodium is actually going to lose an electron and become Na plus. So what's happening is sodium loses an electron to chlorine and then it becomes Na plus. So what is happening over here? Oxidation is loss of electrons, so sodium is getting oxidized. So this is oxidation. Now there's something more to it. Be careful, observe carefully. So now Cl, okay, Cl is a monoatomic or a diatomic? It's a diatomic molecule, right? So first I'm going to write in terms of a single atom of chlorine. I know its Cl is Cl2, okay, but I'm going to write what happens to one chlorine atom. So that chlorine atom is going to do what then? It's going to accept the electron that was lost by the sodium and it is going to change to Cl minus. Now I know that if one chlorine accepts one electron and becomes one Cl minus, then because I know chlorine is diatomic, so in all Cl2 is going to accept 2 electrons, okay. So I'll write Cl2 plus 2E minus gives 2Cl minus. That means Cl2, if it is going to combine with sodium, will require sodium to give it 2 electrons. That means not one sodium atom but 2 sodium atoms have to be involved, because one sodium atom can at a time lose only one electron. So 2 sodium atoms together are going to lose 2 electrons and then are able to form 2 Na plus, right? So only if there are 2 sodium atoms willing to lose 2 electrons, then those 2 electrons will be accepted by the chlorine diatomic molecule to form 2 Cl minus ions, okay. So is this clear? Okay, so these are the half reactions. So I can say first one is the half reaction for sodium and second is the half reaction for chlorine, okay, fine. Okay, Cl2 I can say. Now you can actually add these two half reactions. Okay, so I'm going to just use another color here. So everything to the left is the reactant and the right is the products. So when I'm going to add this, what am I going to do? Imagine this is a mathematical sum. Same way I'm going to add. So I'll write 2Na plus minus 2E minus plus Cl2 plus 2E minus gives you 2Na plus 2Cl minus. So what's happening over here? I am going to straight away cancel these two electrons because NVHs I know they got cancelled. And then what is going to happen here? Let me rewrite this. So it becomes 2Na plus Cl2 gives 2Na plus 2Cl minus. Okay. So in this way, I can actually write the overall reaction as 2Na plus Cl2 gives 2NaCl. And how did I write this 2NaCl? Because I know that the charges are the same. Na has got a plus charge, Cl has got a minus charge. So if I cross them, I get NaCl. Okay. So this is the overall reaction. And the steps are as indicated above. This is how the overall reaction is written. Next example that I've taken is of magnesium reacting with oxygen to form magnesium oxide. Now again we need to write the half reactions. Remember, you can be asked to do all of this in the examination. So the half equations. Okay. So what are the half equations for magnesium and oxygen? Okay. We need to understand that. Now once again, try to recollect from the previous explanation that the oxygen has an atomic number of 8, so its electronic configuration is 2, 6. It just needs to accept 2 electrons to complete its octet. That means its oxidation number is going to be -2, right? So that means one oxygen is going to lose 2 electrons. So if one oxygen is going to lose 2 electrons, okay, and it is going to form O2 minus. Okay, that is for sure. But there is oxygen which is diatomic. So in all, 2 oxygen atoms. Now I can't write 2 oxygen like this. I know it's a diatomic, so I have to write this down as O2. So if one oxygen loses 2 electrons, okay, if one oxygen loses 2 electrons to form O2 minus, I will have a diatomic oxygen losing 4 electrons to form 2O2 minus. That is how it is. Now is this correct? No, it cannot lose. If you have realized this, I'll be very happy. The half reactions for oxygen, okay, the half equation for oxygen, what is it going to be? Oxygen has an electronic configuration of 2, 6. It needs to accept 2 electrons, right? Not lose. Well, if you got that, I'm glad. And if you didn't, be more careful. Sorry for that. Okay. So now, if one oxygen atom is going to accept 2 electrons to form O2 minus, then a diatomic is going to accept 4 electrons to form 2O2 minus. Now that means this is my half equation, okay, the one that I wrote down. Okay, so I'm rewriting this here. O2 plus 4E minus gives you 2O2 minus. Okay, fine. In the same way, now oxygen is going to expect magnesium to lose 4 electrons, right? Because it wants to accept 4 electrons. And because it is reacting with magnesium, magnesium has got no choice but it will have to lose 4 electrons. So but you know that one magnesium is only known to lose 2 electrons, because electronic configuration of magnesium, atomic number of magnesium is 12. So 2, 8, 2. One magnesium can only lose 2 electrons, right? So that means this is the ideal equation. But because oxygen needs 4 electrons, 2 magnesiums will have to in all lose 4 electrons. Okay, and then the right equation is going to be 2mg. 2mg what now? 2mg plus. And 2mg plus or 2mg2 plus? 2mg2 plus. 2mg2 plus. Why? Because one magnesium loses 2 electrons to form Mg2 plus. It forms Mg2 plus because it has lost 2 electrons. Okay, so 2 magnesiums will lose 4 electrons to form 2 Mg2 plus. Okay, so now these are the equations, half equations. Okay, now what do we do? Like I told you in the previous example, we are going to add. Okay, so we are going to add the left hand side and the right hand side to get the overall reaction. So this is going to be Mg plus O2. Okay, I'm just highlighting the arrow here. So Mg plus O2 gives you 2 Mg 2 plus 2 O2 minus. Sorry, that's 2 Mg. Okay, just a minute, I think I messed up here. I'm so sorry. Why did I consider that as the half equation? Okay, this I think I need to erase this now, because by now, or either I should write this down as complete magnesium. Wait, I'll just write this as magnesium. Okay, magnesium and oxygen, so half equations for magnesium. This is better. Okay, sorry for that blunder. Okay, so now this becomes 2 Mg plus O2 gives, so here is my highlighting needed. This is where I'm going to highlight this. Okay, 2 Mg plus O2, and I need to write the electrons. So minus 4e minus plus 4e minus gives you 2 Mg2 plus 2 O2 minus. So the same equation I can write down as, cancelling off these minus 4 electrons, I can write this down as 2 Mg plus O2 gives you 2 Mg2 plus and O2 minus, and this is nothing but 2 Mg plus O2 gives you 2 MgO. Okay, I'm really sorry for confusing you on the top. Even see, I got confused. So it's better, like see, even if it's a teacher or a student, if the work is messy, obviously you are going to face it. So you should learn from my mistake. I actually was not organized in writing the half equation, so I sort of goofed up, but good, I realized. Okay, so this is how you write the overall equation. So whenever you have to explain oxidation reduction in terms of loss or gain of electrons, you're going to do it in this way. Now in this whole process, let me tell you, so in the first sum, if going back to the first sum of sodium chloride, so the half equation in the first one told you that sodium atom lost electrons. 2 sodium atoms lost 2 electrons, so oxidation is loss, that was loss. And the lower one is reduction, because the electrons lost by sodium were gained by chlorine. Okay, and the same way over here, the equation, half equation for magnesium tells you that electrons were lost by magnesium, oxidation is lost, so magnesium got oxidized. So magnesium oxidation, so this is oxidation, and this is an example of reduction. Okay, fine. So this is how you will be using the concept of loss or gain of electrons to identify whether there's an oxidation reduction happening for a species, and the overall redox reaction you need to identify. Okay, and so the last one remaining is oxidation and reduction in terms of hydrogen. So again I will write this oil. So oxidation is loss of hydrogen and reduction is gain of hydrogen. So this is reduction is gain of hydrogen. Okay, this is the last thing that is remaining. Now I'll explain with the help of examples. Okay, so here I have taken 3 examples to explain the concept. So just remember once again that oxidation is loss of hydrogen, reduction is gain of hydrogen. So now in this case 2NH3 plus 3Br2 gives you N2 plus 6HBr. That is your balanced equation for the reaction between ammonia and bromine gas. So what's happening? Look at ammonia. Ammonia has 3 hydrogens, okay, but when it changes to nitrogen and HBr, the change is obvious that here, if I consider these two, then I can say that a hydrogen has been lost by ammonia. Okay, so clearly you can see the hydrogen disappeared from ammonia, so therefore this is loss of hydrogen and therefore it is an example of oxidation. Similarly, when you look at Br2 and HBr, now there is a hydrogen connected to bromine and therefore it is gain of hydrogen and therefore it is reduction. So reduction is gain of hydrogen, so Br2 is getting reduced and NH3 is getting oxidized. So this is oxidation reduction. Now another thing, if you look at the reaction between H2S, hydrogen sulfide, and chlorine gas, what's happening? Okay, pause the video, try to solve it on your own. Okay, now continuing. So if you have H2 gas, okay, reacting with Cl2 gas, what's happening is the H2S gas, if you compare this with sulfur, the H2S gas is getting oxidized. Why is it getting oxidized? Because oxidation is loss. It doesn't matter if I write oxidized, but I'm following a particular procedure, so I'm just writing it down that way. So oxidation. So there's oxidation happening for H2S. It is getting oxidized from H2S to S, which is sulfur, and chlorine at the same time is undergoing reduction because chlorine has gained that hydrogen. So this is reduction here. And the last example over here is the copper oxide and ammonia. So when copper oxide reacts with ammonia, it forms copper, nitrogen gas and water. So consider copper oxide and copper. What's happening? Okay, now over here, if you can consider this reaction, okay, there's loss of oxygen. Okay, not hydrogen actually, there's loss of oxygen. So what's happening over here? Copper oxide is losing oxygen, okay, it is getting reduced. Now ammonia, look at ammonia and look at nitrogen. So now look at ammonia and consider this nitrogen. What has happened? Ammonia has lost its hydrogen. So ammonia has lost its hydrogen, so it has got oxidized in the process. So this is oxidation. So beautiful example where you have a loss of oxygen and you have a loss of hydrogen. Okay, so this is how you can actually explain the oxidation reduction in terms of either electrons, oxidation numbers, your oxygen, or the oxidation states. Okay, so these are the 4 methods and you will be asked in your examinations, and this is also a very important video for IBDP kids because they also have it in their syllabus. Okay, and this covers a large number of concepts. Even for the A levels is going to help. So basically this is a foundation for chemistry for any student, maybe any board rather, not only international, but yes, it's meant for the international syllabus basically. So that is all. And one more thing I would like to talk about is I forgot to talk about this important concept, which is the oxidizing and reducing agent. So oxidizing agent and reducing agent. So whom do I call as an oxidizing agent and whom do I call as a reducing agent? Well, oxidizing agent is someone that oxidizes the other element, okay, and itself gets reduced. So it is a substance that oxidizes other substance. So how do you define an oxidizing agent? I'll just write it down here quickly. So here are the quick definitions, and the definitions say that oxidizing agent, it is a substance that oxidizes other substances and gets reduced in the process. And a reducing agent is a substance that reduces other substances or substance and gets oxidized in the process. So technically speaking, it's very simple to understand. The one that is an oxidizing agent will oxidize some other substance but itself get reduced, and reducing agent will reduce some other substance and itself will get oxidized. Now let me just consider the case of, say, hydrogen sulfide, the reaction here. Okay, this reaction here, just let's consider one example and rest is just self-explanatory. So here what is happening is hydrogen sulfide, okay, what is happening to hydrogen sulfide? It undergoes oxidation. So itself it undergoes oxidation, so definitely hydrogen sulfide is going to be my reducing agent. Because the one that gets oxidized itself is the reducing agent and Cl2 is getting reduced, so therefore it's going to be the oxidizing agent. Okay, the same is true for the others also. The one that gets reduced is always the oxidizing agent and the one that gets oxidized is the reducing agent. Okay, so you can do it for the other sums also later on. Well, so that's all in today's video, and I try to cover as many things as possible. Okay, so please see that you revise through the video. Whenever you revise through the video, try making your own notes, try solving whatever equations I put on the screen, identify the reducing oxidizing agents. Okay, and it's not at all difficult, it's very simple. Only thing is your concept should be clear. Once your concepts are clear, nothing is difficult, trust me. Okay, so well, that's all in today's video on oxidation, reduction and redox equations. And if you do like watching my video, please do subscribe to my channel. Thank you.